So again, all right, time dependent, hard stuff, this stuff, a little intense right now. I think last time it was just a bunch of algebra. But I can't dramatically emphasize enough that creation, let me write this down. Sorry, so technically it's annihilation. Annihilation operator. I see these all the time. So obviously we're talking about vibration, which is really important for a whole bunch of stuff. But it is I see it in so many other places. Now one reason is that solids, and again, I am very concerned about solid state quantum, because solid state inorganic chemistry, the importance of that field is just exponentially rising, because that's where we get catalysts that extend the life of petrochem, which is finite. We're still driving cars. Catalysts that may turn water to hydrogen. So all of a sudden, material science is just so. It was so screwed up is that a lot of departments do not teach solid state electronic structure. At least chemistry departments. Maybe I'm sure physics probably does, but we don't. And that's messed up because we're the ones who make the stuff. Anyway, now remember that the creation is technically the transpose of the annihilation. Let's keep them straight. That's the transpose, right? Now I looked up. Now remember, I had always said from the very beginning ad nauseum that it's never really clear how to define a transpose. Unless it's Hermitian, then you don't worry about it. If it's unitary, then this is one over that because they're one with multiplied. In this case, I actually did look up how you derive this from that, and it was kind of interesting. It's basically something like this that you might want to know this. But here's an operator. I usually do it this way, right? So the way you define a transpose is that these are equal. Yeah, it's like that. Now, the way I would do this, I would imagine that I would be resolving identities and whatnot. So in this case, what I was reading online was, and I'm working on it, so I might put this in your homework. But I was working out exactly how to solve this. In the case of a derivative, then the transpose is minus derivative minus derivative. Blah, blah, blah. Okay. Now, of course, you can see that here. Momentum is a derivative, so you can see the transpose as a minus sign. Anyway, so that's where that comes from. I don't want to throw stuff at you. I've always been annoyed about how transposes are defined, and apparently it's this. So anyway, I was actually scribbling some notes. I was trying to figure out how you prove that. I'd put that on homework. That'll just be some math practice for you to do. It actually looks relatively easy. Okay, so there's that. And then we define the number operator somewhere here in my notes. Okay, so still just reviewing. It's really easy once you A cross A. Okay, there's that. And because of the way X and P, over here, remind yourself, Hamiltonian is P squared over 2M. I remember I was messing this up a little bit last time. 1/2 M. I just have to have right. Okay, between all this, what we're able to do is show that the Hamiltonian, so therefore the Hamiltonian Hamiltonian is, so I know it was, again, yesterday, or Monday, sorry, that was, I felt, definitely one of the more intense lectures. And it really, it was just a bunch of algebra, but it was a lot of algebra. And this is what we had come up with. And although I realized maybe I was a little out of order, and there was also other identities that we need intensely today, which was that we had some commutator relationships, because you keep saying how we do a derivation and somehow we manage to reduce something to a commutator. And of course, if you write the commutator backward, then it's just equal to minus itself. Because AB minus BA is minus BA minus AB. So, fifth grade algebra, let's see. Okay, all right, so that's just a review of what we did. Those are a bunch of identities. And again, it was just algebra after algebra, just never. Anyway, yeah, sorry, I was talking about why these are important. Other than vibration, solid state vibration, which instead of just calling it vibration, you call them phonons. They also work. I always see those with creation and annihilation operators. And solid state phonons, understanding phonons for the solid state is terribly important for a whole bunch of reasons. The reasons, think about why is conduction finite? Why do we have resistance? Because electron, I don't think anyone really understands this that well, but an electron, the terminology is the electron scatters off the phonon. What that means is that the electron is going through the wire, but it takes a right turn, and in the process creates a phonon, or maybe it eats one up, conservation of whatever, momentum, energy. So when it comes to understanding why things have finite conduction or why are things superconductors, you need to understand how electrons and phonons interact, and guess what? You're going to run into those. So anyway, that's why they're so important. Okay. All right, nitty gritty. So since the Hamiltonian is a function of the n operator, they commute, and we've seen that a gazillion times. Operators and functions of operators commute. Again, that's fifth grade simple actually. Okay, so now let's define a ket for n to work on, and let's. Now it looks like, be careful that it looks like I'm making a decision as to what these states are and eigenvalues. I've said n, it sounds like n's an integer because we often use the letter n for integer. So the eigenvalue is an integer. I haven't said that, but that's actually exactly what it is. But anyway, but I haven't decided that yet. I am going to prove that. And how do I do that? Okay, so I have to admit, so again today, heads up, we're going to have a mess of algebra. Okay, so let's act on the left with a bra. And of course, we'll assume that the state is normalized so that the inner product of n with itself is just 1, which is reasonable. Okay. Now, here we go. Notice that I have the bra being acted on with the transpose of the annihilation operator. So I can do this. And I know that this is going to have some result. This is going to have some other result. Sorry, I'm yeah. So let's a C for a constant, right? So of course, this being the transpose, okay, so this operator on the end is going to return some kind of number. And remember that C and N are not the same thing, right? This is a distinct operator. This is the N operator. So I've broken it up into pieces. So I don't necessarily know what the relationship between N and C are, although I'm determining that right now. This being the transpose, of course, it just returns the complex conjugate of the same number. And now what I've got is, hopefully if I can read my notes, well, it would just be just the absolute value C squared and N, I brought it down for itself. Okay. So what you get from this is that, sorry, again, small word. N is a positive number. And let me just cut to the chase, just so you can kind of get an idea why I'm doing any of this. So basically, this N is going to report the quantum number of the harmonic oscillator state, which will be 0, 1, 2, 3, 4, 5, blah, blah, blah. Right, so that's why this is actually a whole number. I'm actually just going about proving it. I know it's like cheating to tell you ahead of time what I'm trying to do, but here we go. Okay, now what we have to do is derive, now this is really kind of ridiculous, so now we have to derive more commutation relationships, and what we're going to do is ultimately, and I've already told you what the end goal is. The way to get to the end goal is I am slowly going to whittle away at properties of these eigenvalues. I'm gonna force them to have certain properties such that that N has to be 0, 1, 2, 3, 4, 5. That's what I'm slowly doing. Okay, and remember that the book, I'm just kind of faithfully reproducing the book here. For the book's wonky, this part is maybe not as bad as others. Okay, again, as I slowly pigeonhole the N eigenvalue with certain properties that force it to be an integer, I'm going to have to go about calculating a bunch of commutators, and then I'll put them all together. At the end, I may forget the little hat, I'm so good about that. Okay. Now, one thing about a commutator is that you can factor, if you write the whole thing out, and I don't want to do that because, again, I'll barely finish this if I'm very lucky. If you write the whole thing out, you can find that there's little algebraic proofs, basically. So this is one of them. Your book lists all of the algebraic properties of commutators somewhere in it. So I'm just kind of writing that down. Well, that's a commutator with itself. So again, just write this out. This times that times this, and you'll find that you can factor it into this form. And that's nice because I've actually simplified it a little bit. And I have, see, I have this one right there, right? So you can see I can simplify that. And then you've got, of course, let's do that with the creation operator. And what you find is going to be a plus. That's a creation. And, I'm not a big fan of trying to memorize these identities of commutators. Obviously, that goes to 0. That's the commutator of the thing with itself. We did this yesterday. It's 1, so this is a big it's creation operator. Okay, okay, now that I have this defined, now I'm going to write some more stuff down using all these identities and slowly force n. I'm not only going to force n to be an integer based on its properties, I'm also going to be able to define the creation and annihilation. It sounds like, again, it sounds like I already have, right? I've already given them names, so you probably already know what they're going to do, but we're going to prove that. So that's another part of what we're doing here. Okay, so more stuff, more just writing things down that are like, what the heck? You know, just, it's like a smorgasbord of just writing things down. So what I'm going to do is I'm going to say the operator is equal to itself minus plus some other whatever. What I see now is that this is equal to that little trick of adding 0, right? So this is the commutator of creation. Okay, so now what we do is now we're going to start figuring out what happens to the kets. And so we've got, actually I kind of did something stupid. What I did that was a little stupid, is that I have this defined right there. Okay, so this ends up being a, yeah, look at that, it ends up being a plus, right, creation plus creation number. And that means I can factor that. 1 plus n. That bothers me. That has to look much better. Okay, and so this ends up being n plus 1. So I just basically wrote this down, and I got it equal to this. So notice that, therefore, let me write it all down again. Because it's probably not clear at all what just happened. Notice that you can kind of think of this as its own state. So, and don't forget, I should have brought this up earlier. One of the things we had covered when we first started doing the Iraq notation, or operators in general, was that operators turn kets into other kets. So it's still a state, right? And this happens to be an eigen, I'll use the proper term, eigenket of n. And n plus 1 is its eigenvalue. Okay, so again, a bunch of really massively non-intuitive jumble of letters and everything we can do with them has yielded this result. The point of this is that I can now see what the oddly named creation operator does. Whatever it's going to do with this state, the number operator reports n plus 1 of the original state. So it looks like, you know, it's like turning this state, and it's turning it into another state, the eigenvalue of which is n plus 1. So you can imagine that the creation operator on the n ket, turns into the n plus 1 ket. And again, I'll prove that in a minute. So again, if the creation operator on n returns the n plus 1 ket, that would make a lot of sense, because the number operator on n plus 1 ket would return n plus 1 eigenvalue, as defined here. All right? So there you go. Okay, now I have to go over here because I'm out of room. Notice I did that with the creation, now I need to do it with annihilation, and I'll be brief on this one. I'm actually almost lost in my own notes. Okay, so let's see what annihilation does. This is going to turn into, oh, sorry, that was ugly. Okay, it is going to be, for all the same kind of silly algebraic manipulation, adding creation number, subtracting creation number gives me this. Okay, I'll be able to factor out the annihilation, but this, where is it?
They're -8 and. No,
Yeah.
just lower.
Huh? Oh, yeah. Yeah, you see that? Yeah. So I'm factoring out the annihilation operator, but there's a minus sign in front of it. Sorry, I'm just a little blind a little. Okay, so same deal. So again, let me just summarize. So the annihilation operator acting on n, while I'm still trying to figure out what that's going to do, I know that the n operator, the number operator, whatever the heck the annihilation likes to do to n, the number operator reports n minus 1. So again, it's not hard to intuit that the annihilation operator on the ket is going to turn it to the n minus 1 ket. In fact, it kind of has to be like that, right? Okay. So now what we're going to do is just all over the place, isn't it? I don't know. I should look through this, see if there's a more coherent way to do this. I mean, it's kind of nuts. Let's work on these. Let's work on the seeds. All right. So let's figure out what the seeds are, and then we'll put it all together at the very end. Okay. So that's more stuff. Jesus, this is crazy. I'm just struggling. Well, I just wonder if we can get through this. Yeah. So let's summarize this stuff. So we can go ahead and say that a plus on n is going to be some kind of constant. N plus 1 can be annihilation operator on n is going to be some kind of constant. And minus 1. Now what we're going to try to do is, again, I pointed that out here, constants, right? I have to define those. So let's figure out what those are. And, okay, so how am I going to do this? Okay, so we have to go back. Let's go back here. We're going to kind of separate this. So that it's obvious that this is. Oops, absolutely right. So we've already done this. Remember, this proves that n is a. Oh, wait a minute, wait. No, I messed this up. I didn't do that right. You see what's going to happen? Okay, so the annihilation operator on this can be n minus 1. Okay, but what's the, creation operator gonna do on that bra?
As well as
Like check conjugate.
It's the that's a bra. What does it do to a bra? Yeah, N minus one. Gets you, doesn't it? Then you gotta reverse what it does, remember? Remember, whatever a ket does to, whatever an operator does to a ket, the transpose does the same thing just on a bra. Now you're saying N plus one, but that's what this does on a ket. Which is weird because we never had transposes act on kets before. You're seeing that for the first time. I mean, I can do it. I just never did. That's crazy. So, but here we're able to do it. Yeah, here we're able to do it. Gets you, doesn't it? So I screwed this up. Well, I mean, I didn't, but anyway, so you saw what I did, sorry. Okay, so there's that. Okay, so therefore, now this is where there's actually a slight problem with the proof. I think the book admits that. Right, you know, yeah, I mean, like, right, so I'm here. And what is that? That C minus C can be, yeah, C can be plus or minus square root of it, right? But we're just going to call it this. So this is like the one whole proof, and it's a pretty small concern. Okay, so there's that. And so now we can say, therefore, that the A operating on N is square root of N. Now, remember that I basically, although I had the creation operator here, I basically thought of it as the annihilation operator acting on draw, because I did that. So this C is really the C belonging to the annihilation operator. So that's square root of N. Okay, now I am going to reverse this. I'm going to reverse this and figure out what creation does. I'm going to have the transpose act on the ket instead of the bra. Again, something I kind of hinted like you should never do, but if you recall, I said that it was actually just tricky if you just wanted to avoid it, and not that you couldn't do it. Okay, now before I started, you know, so basically I said this was, sorry to wipe this out here, C, but now what I want to do here is actually, they're not necessarily the same constant, so yeah, I shouldn't wipe that out. Let me just do it here. Now again, I've already proved that the creation operator bumps up the state by 1 because of the way the number operator tells me that. Okay, so now what am I going to do? Okay, kind of the same thing. N. I'm going to have the annihilation operator. And I'm going to have the creation operator. And again, I'm trying to kind of guide your eye. These parentheses are meant to guide your eye. And what I end up with is whatever t squared is. So creation on N bumps it up 1, annihilation. We're working on the bra is the transpose of the transpose. So that bumps up the bra. Remember, it lowers the ket, it raises the bra. It does. I've done this right, so just in case you're concerned. I had to stare at this for like an hour by the way before class. Okay, God, how do I do this? Okay, so this next one. Okay. Now get this. Get this. This is, of all the things that have been kind of BSy, this is, this is one of the worst. Okay, it turns out that, here's what I'm going to do. I'm going to write A, here it is, right in the middle. And then I've added and subtracted that guy. And the reason I've done that is, this is, sorry, that's, that's my number operator, right?
Yeah.
Is it A star? Yeah, that's number operator. Yeah, it is. So there we go. And, okay, and then this is oddly still there. I remember we did that last time. Okay, so now, notice I'm not going to write parentheses. So I'm back here. And now what I can do is this. Okay, so therefore, E squared is n plus 1. Therefore, the creation operator on n does this. It returns the square root of n plus 1. So there we go. Okay. All right. And let me summarize that with also this statement here. So this is kind of a big deal right here. So this is really a good bit of really what I was trying to do. Show what creation and annihilation operators do, what was the most ridiculously convoluted whatever I've ever seen in my entire life. Remember, it really was a bunch of algebra, right? Did you see me integrate anything or take a derivative, right? How hard would that be? But I didn't even do that. It was just, geez, it's just a mess. Anyway, I don't know if there's a better way to do this. I would just stare at this for like 5 hours, maybe I'll figure it out. But anyway, so you see what creation does. You see what annihilation does. And I can tell you that these eigenvalues, I know one or two applications where these results are significant, and I'll actually show you. I'll show you one. It's kind of interesting why these eigenvalues are important. But reality is, it's just bumping these things up and down. Now the last bit, the book then mentions that the n is an integer, and I have to admit, this one has me, I have tried my best to make sure I understand what the heck is going on. I can just repeat it and hope that you don't notice that I don't have a clue. But so this is a time I'm a little bit confused. Okay, so the book now wants to show, why am I doing that? N is an integer. Okay, why is that? Okay, the idea was to take the annihilation operator and annihilate k times, annihilate k times an n. So you're going to get the square root, right? So you can see that here, square root. Now you can only do this as we're not going to drive this below 0, right? So you end up with this. Sorry, what's the cat? Okay. And here's the idea. An operator having like a body, right? It's like x minus p. You really couldn't raise that. I don't know how you take the square root of an operator. It actually comes up sometimes. But for the most part, if you're going to apply an operator and again and again and again, it's going to need to be, k is going to need to be an integer. You know, apply the same operator over and over again implies k is an integer. Okay, what can happen is, if n was itself not an integer, you could run into the case if n was not an integer, then this could be imaginary. So it's something like that. Again, I'm actually a little bit confused. But if again, if n was not an integer, somehow you can get a minus sign in there. I actually don't quite see it. I'm a little bit lost about why he's saying that. I've tried plugging in numbers and I got myself pretty confused. But anyway, the idea is that you're gonna violate all these rules by doing this k times on n. You'll violate all the rules if n is anything other than an integer. That's the big picture. But I have to admit, I think I actually understand every bit of the stuff I've shown you, except this thing right here. This is the one thing I've gotten kind of lost. So there you go. So I've defined everything you could ever want to know about harmonic oscillators through these annihilation and creation operators. Fun, huh? All right, let me prove that. Okay, x. Notice that from the way I had defined these before, you can isolate x and p. I'll have you do something with this on your homework. Now remember, I hope you had seen this in your undergrad, but spectroscopic selection rules are basically, spectroscopy, you're going to have a final state and an initial state, where the final state is higher in energy. Don't make that transpose. It's transpose minus A, not transpose plus A. So one of the things I hope you had learned in your undergrad was that spectroscopy, an absorption intensity is due to the dipole operator, which let's just call it x. So you have the final state, you have the dipole operator, which is just basically x. It tells you how far the electrons get polarized in the process of transition. And you have an initial state, of course you would square that. So while the x operator has been important just because it's the x operator, momentum is important because actually a conservation of momentum, so you want to know your momentum for spectroscopy. Your absorption intensity is actually proportional to this thing right here. And notice that now I've got this defined in terms of annihilation and creation operators. So that's kind of a big deal. Okay, so I'm just pointing that out. Okay, what else can we do? So these are, right, think of all the problems you've had, we've always just been coming down, hey, what's xp, what's x squared, what's p squared, right? Well, now it's got to be defined. Okay, so let me point out that in the case of n prime annihilation, what you've got is, okay, we're going to operate on n, so that the square root of n is an eigenvalue. We've left n prime alone. Now, assuming that these are orthogonal states, you've got yourself if that's 2, that's got to be 3. See what I mean? If that's a 2, that's got to be 3, because this damn thing is going to turn that 3 into a 2. So, all right, so kind of simple. Okay, likewise, let's see what creation does. Dot. And that's going to be n plus 1. Okay, so if that's a 2, that better be a 1, because that 1's going to become a 2, and then I've got an overlap of the state with itself. And if we don't have that, then it's 0. Okay, so now, if you're trying to figure out, or let's say the ground state, let's say n equals 0. You see why this is important? You might want to now look up the ground state wave function, which is e to the minus x squared. Plug into Mathematica. Or if n prime and n are the same, what do we get? What do we get? 0. If n and n prime are the same, that's 0. N minus 1 and n prime are the same, but I didn't say that. I said these are the same. 0. Okay, that's for annihilation. For creation, this better be plus that, but it can't. It's the same. So what is NA? So NaN is 0, Na plus n is, right, you see that, right? The only way for these things to not be 0 is if these are not the same state. They have to differ by 1 excitation. So if you're doing your normal expectation value of integrate ground state x complex conjugate ground state, what's their average position, you automatically should be able to see it's 0. But then again, you remember your harmonic oscillator ground states, right? Remember that the idea is that the x coordinate is actually a displacement from the equilibrium bond position. So this is an expansion, that's a compression. On average, you're at your equilibrium. So that's what x represents. Okay. Let's do the same trick with p. Remember, sometimes it's good to just go with your gut. Given that p is also a function of creation and annihilation, 0. Note that if it was non-zero, that this vibration, if it's positive, at some point the bond will just start expanding forever. That's what it would mean to have an expectation momentum of positive. It means the damn thing will actually start to expand forever. Not much of a bond. If it was negative, that means it compresses forever, which is even a worse problem, so that's not true. So for the most part, the bond is going to stay about its equilibrium value. That's again a wordy explanation of this equation. Okay, last bit, and we're basically done. I'm not going to, so it's time, and I'm trying to be better about this. let me show you what we're gonna do next, and I'll just bring this up at the beginning of next class, and we're gonna go in a different direction next class. Here's a neat thing you can do. You can do this. Right? Now, of course, A is, I'm just defining the annihilation operator. And then, of course, what you can imagine we can do is resolve an identity. Well, what you're going to do is you'll actually do something like this. Anyway, I'll do this next time. When I do this, what I'm going to have is a diffie cube. You see where I'm going with this? I have x plus derivative of x times the wave function. You can kind of see how this is going to turn into anyway. I'm going to have x times the wave function plus the derivative of the wave function is equal to 0. What do you call that? It's a diffie cube, right? And it's not, so how do you solve the Schrodinger equation normally? It's a second order differential, right? Because it's a freaking momentum operator. This is a first order differential equation. So in other words, what I've done here, I'm writing a first order differential equation to solve the harmonic oscillator, which is always a gazillion, trillion times easier than a second order differential equation. Excuse me. All right, so next time I'm going to start here, act on the left with x so that we project it into real space. The diffie cube is unbelievably easy, so you know. Do you remember this? Remember the solution? Yeah. That's the solution. So anyway, all right, we'll do that next time. That'll be a video over review, and then we'll be off to something new, and I'll make sure that I